Hello all, welcome to my YouTube channel. So in today's video, we are going to discuss about the technology behind the ChatGPT. As we already know, on a ChatGPT, we simply provide the input or any sentence and we will get the response from the ChatGPT, whatever we have asked as an input. But do we know how basically ChatGPT is working behind the scene? What is happening in the background? What kind of model it's using to generate the output? That's what we are going to discuss in this particular video. The term GPT is basically each character G, P or T has their own meanings or own task. The first one here we have a generative, the second we have a pre-trained, and the third one we have a transformers. The first one is generative, which is basically a auto-regressive language model. So generative is also a kind of language model which is used in a GPT. So what it is basically auto-regressive language model here. So auto-regressive language model is kind of a language model which is used in natural processing language to generate the text by predicting the next word. Second term here we have pre-trained. So as the name itself says, this is already a previously trained by a Google which has lot of data sets, millions of or billions of data sets is already have. That's what whatever the prompt or the input we are giving, it's giving us an output as in a response as a back, because it's already trained with lot of parameters. Third one here we have is transformers. So transformer is basically the underlying architecture of GPT, ChatGPT. So now in this video we are more majorly focusing on the transformer part. What kind of model we have or architecture we have transformer, and what part of transformer architecture is mainly used by the ChatGPT. So this is what we are going to discuss. So before moving to the transformer architecture, let's see the history of ChatGPT. So the first version or initial version, which was GPT-1, was released in 2018, which has 117 million parameters. This is what I meant in the previous slide of pre-trained. It's all that model is already trained by these many parameters. The second version, which was released in 2019, is GPT-2, which has 1.5 billion parameters. If you can see the difference between ChatGPT 1 and 2, there are almost 100 or 100 times parameters we have in GPT-2. Next version we have not 100 times exactly, but more than 5x mostly. Now the third version we have here is GPT-3, which was released in 2020 and it has 175 billion parameters. You can see now here we have 100x more parameters in GPT-3. The fourth version is not officially released because there is no documentation, there is no document published. It kind of a basically we can say a iteration of between 3 and 4, which was GPT 3.5, and that was launched in 2022 and 2023 between. And there is no official documentation about the how many parameters we have in GPT 3.4, but it's somewhere around between 3 and 4 we have the parameter. It is more than 3 and less than GPT-4. Those that many parameters we have. That's why I have written here is NA, not available. The fourth version here we have GPT-4, which was launched in 2023 and that has 1.76 trillion parameters. So as we can think how much this particular latest model of GPT is trained, because it has almost trillions of parameters, data sets it already trained. Now move to the transformer architecture. So the transformer architecture was introduced by a team of researchers at Google Brain Division in 2017, which was paper titled "Attention is all you need." This is the paper which was published by the Google. Attention is all you need. There basically it defined this particular architecture. So the transformer architecture consists of an encoder and decoder structure. So you can see this particular part is encoder and this particular part is decoder. What GPT is only used the decoder part only. Decoder only part is used by the chat GPT. There are other AI models which use both encoder and decoder model, but chat GPT is only used decoder only part of this architecture. So that's what we are going to discuss, how this decoder only part is working behind the chat GPT. So that's the framework which we are going to discuss in more detail. So let's move to new slide, next slide, sorry. So this is the decoder only transformer architecture. You can see there are multiple layers and each layer has their own job or own purpose. So these all the layers we are going to see in a more detail in the coming slides. But for now, we will just see what each layer is doing here. So the first one here we have is input token. Input token, like initially when we type anything on ChatGPT, okay, I want anything about this topic, then we will get a response. But with between input and output which we got, there are so many functions or so many tasks which is happening in a background which we are not aware. So the initial thing is input token. So here, for example, I have typed chat GPT is great. This is the input which I have provided to the chat GPT. Now the chat GPT start working in backend, and in the last it will give us a output. So there are so many mathematical calculations which it do based on the tokens or words. So that's what we are going to discuss in more detail. But for as of now, just focus on these all the layers which is used by the decoder only structure, and next slide we will explain, I will explain each layer and what is doing, and few of the layers we will do in real time also, how basically it's doing. So the input token, as we know, simply we provide the input to ChatGPT. ChatGPT is great. The second, what it does, token embedding. So whatever the chat or whatever the sentence we provide to the ChatGPT, it basically tokenize everything. It could be based on each character or each word. It will start tokenizing those words, because in real time or systems or programs will not understand the word. It's basically understand the token part. So for example, chat is could be a one token, G will be a second token, P will be third token, or T will be a fourth token. Or it could be a chat GPT can also be a C, H, A, T will have their own single tokens. That is the calculation which basically chat GPT do. Now the third layer we have is positional encoding. So what it does basically, because the token which we are receiving from the token embedding layer, the ChatGPT, the transformer decoder model will not be aware, okay, in what sequence we need those parameters, those tokens. So it will add some kind of vector on each token, and it will positionize all token based on some formulas which we will see. The third here is self-attention mechanism. So attention, again here there are some mathematical calculation which is happening based on the tokens or vectors which we have encoded in the positional layer. So based on the attention score and weighted sum, it will analyze, okay, this token will have high weightage, this token will have low weightage. So like that it will basically understand self-attention mechanism. Suppose for example, if we are reading any book, and we will not focus on each of the word, what we will do, suppose we have read the life is good, we will measure, most probably we will focus on life and good. It means we will self attention. So we are not focusing on self is life is good, each word, we are simply focusing on the entire word, and based on some metrics or based on our understanding, we will aware, okay, this is that is the meaning of this word. So that is what called self attention mechanism in decoder only model. The third we have here is multi-head attention. So multiple attention head. So this is not like a single person if I share in a real life example, might be there are four persons sitting, and four persons will be focusing on some other parts of that particular object or things, and they will decide from their own mindset. Okay, this what will be the this will be that will be the meaning of this particular object or this particular sentence. That's what a multi-head attention is doing here. Next, here we have here add and normalize layer, feed forward neural network layer. Again, we can see here is add and normalize layer. So these are the few layers which is repeated in after each layer, and this mechanism is happening repeated n times until it will get the proper response, proper output, what we want in a real time basically. Then we have a linear transformation and output probabilities. So finally we will get the output after going through each and every layers. Finally we will get the output. So let's understand each layer in more detail. So the first layer was input token. I'll do, I'll go back to the architecture as well in time to time. So the first one was input token. So description, what is does, these are the raw textual inputs that the model received. It means we are providing the input to the ChatGPT model. In GPT model, text is broken down into smaller units called tokens, which could be word or subword. So as we discussed ChatGPT, chat could be the one word, GPT or it could be the separate tokens. So for this sentence, ChatGPT is great, the token might be ChatGPT is great. That this might be the token for this particular sentence which we have provided, ChatGPT is great. So let's say in a practical way, I have created a few Python scripts which basically help us to understand more how basically these particular things is working. So let me open the scripts here. So these are the scripts which we have, few scripts. I'm not going to explain each and every layer with a practical demo. Few layers have already Python scripts, so that's what we are going to discuss. So the first here we have is input token. So let me open the command prompt, not actually command prompt. Okay, let me open the command prompt here. Let me run the script. Oh, so input token. So you can see the token is ChatGPT. So if I'll edit this particular file, so here the sentence I have provided ChatGPT. Let me provide here ChatGPT is great, and let me save it. Now again I'll go back and open my command prompt, and here again I run the Python script. So now you can see the token it's included ChatGPT is great. If we have a very lengthy sentence, then it might break the token in much more, like it could be the ChatGPT 1, I will be the one other token, S will be the another token. So like that the input token work. So I hope it's clear. So let me go back, close this, and okay. So the second layer we have here is so the primary function of token embedding layer is convert the each discrete token which is received from the input token layer and convert into the dense vector of the fixed size. So this conversion basically allows the model to work with the numerical data and capture the semantic meaning of a token in a way that is useful for the model to learn and make predictions. So this is, you can see the example here, the token is might be chat. So chat is a token which is received from the input token layer, and it might be converted to the dimensional vector. There are many dimensional vector, like it could be 8-dimensional vector, 16-dimensional vector. So that's how this dimensional vector is used So we can use any kind of dimensional vector. For this particular demo, I might use 8-dimensional or 6-dimensional vector. So to keep things very simple, but in real time, Google, the ChatGPT model is used much more very large dimensional vector here. So let's understand how basically the ChatGPT version is token embedding is happening in a real time. So let me go to the script file. So this is the script file for token embedding. Let me edit it. So you can see here the text data here I have ChatGPT is great. Again the same sentence I have used which I have used in the input token layer. So now we will see how this token embedding is working for this particular sentence. So let me close this. Let me go to my command prompt. So I'll run the script Python. Let me clear the console. And the script file name here is name is token embedding. Okay, T is caps. So now you can see this is the dense vector. Basically, it is created by the word ChatGPT is great. So if I count here the tokenized text data here, this is the embedded format of each like 67, 104. So these are the embedded format. And if I see here the chat is has CHAT. This is chat. Now we have GPT. Then we have is great, GREAT, and we also have the space between the word. So that's how basically it tokenize the data. ChatGPT is great, and for each token it generated the embedded text data. So this is in a AI or machine learning format because the model understands these particular embedded tokens. It will not understand the simple format of the text. So that's what the token embed. That's how basically a token embedding work here. So each token has their own some kind of formats. If I go back to my slides here, that's why you can see. Okay, let me go back. So you can see the chat might be converted to the 512 dimensional vector, and the format you can see this 0 0.1, 0 0.2, 0 0.05. So this is how basically a token the input token is embedded in the token embedding layer. Now the third we have here is positional encoding. So what happened in basically positional encoding, the decoder model which we are using in ChatGPT that doesn't understand the sequence of the tokens. So that's why it adds some kind of positions in the tokens, so it will understand why the decoder model in a sequence. That's what I have written over the slides. So in a decoder model, decoder only transformer, positional encoding is crucial for providing the model with information about the order of token in a sequence. So what is happening, the token which we are getting from the token embedding layer, that token is provide to the in a positional encoding provide token in a sequence basically, since the decoder process the entire sequence at once and doesn't inherently understand the position of each token. That's why positional encoding help the model and utilize the sequential information. So positional encoding can be sine and cosine functions. There are few mathematics function which is used by the positional encoding format. So for the first token in a sequence, a positional vector, the first token was chat. So the positional vector could be this format is added to the embedding vector. So let me go back to my script file. Let's see how basically this positional embedding is working. So I am here. This is the script file for positional encoding. Let me edit this file. So this is the complete sample Python script file which I am gonna use here. So let me focus on what is the sentence I have provided on this file. So the sentence we have here is, so here the sentence simply I will tokenize the sentence chat. So in positional encoding, what we are doing, we are following each task. The first step, tokenize the sentence. The second, create the token embedding, and the third, we are doing apply positional embedding on this that particular input token. So all these three steps will be done as part of this particular what is called on this layer. That's what we are going to see. So let me make it here also. Chat is great. Sorry, chat GPT is great. Let me save here. So you can see here the D model, which is dimensional, what is called dimensional vector, which we are using here 16. So in a slide you have seen 5, 1, 2 dimensional, but here we are using 16. So it will easy to understand in this demo. So let me close it. Now I'll go to my command prompt again. Let me clear the screen. Python, this is the file name which we have, positional encoding example. So let me run it. So now you can see the first thing what is happening here, token embedding. The second layer we have here is positional encoding, and the third layer we have here is encoded token, which is a combination of embedding and positional encoding. So this is the output of these layer we will get it. So I have visualized this particular diagram. If you can see here, this is what we are going to discuss in a coming slide. Let me okay, so now it's more clear. So you can see here the token position. The token was ChatGPT is great. Here also we can see ChatGPT is great. So this is the token position, and this kind of particular let me go back to my slides again. There I have already discussed this particular diagram. So let me go back. Okay, so here we have, this is what we have seen in the visualization. So what is happening here? This is the token positions here we have, and this is the x-axis where we are seeing embedding dimension, and this is the token positions. So let me go back to one more slide ahead. So here you can see visualization explanation. So that particular image consists 3 heat maps. The first heat map here we have is token embedding. This is the first heat map. The second heat map here we have is positional encoding, and the third heat map here we have is encoded token, which is embedding plus positional encoding. So these 3 heat map is generated by that script basically. So what each layer is doing here. So the token embedding, this heat map shows the embedding for each token. Chat is great in this sentence. So y axis represent the token position labeled with the actual token chat is great, and x axis represent the embedding dimension, which is 1 to 16. In a script I have shown you, we are using a 16 dimension model. So if I go back to my screen here, so you can see the embedded dimension here we have 16, and the token position which we have in the y axis. So each token you can see chat is great. If I open the diagram again, so you can see okay. So if I'll minimize this, so you can see some kind of you can, okay, let me make zoom. I'm not able to zoom it. So you can see here, if I'm pointing somewhere on this particular diagram, you can see in a down x, y is some configuration you will see here, x axis or y axis. The So if I'll, for example, if I point it here, you can see x here we are getting 15 and y 16. So this some kind of formula basically is used in a background to achieve these particular things. So I'm not going to more detail because for us on a real time, that is not much more important, like how basically this calculation is working, because this is already done by Google, and they have provided us a tool and we are simply using it. But we should also aware what kind of technology or algorithm or architecture or model is using by Google in a background. So let me close this. Let me move to the second next layer. So the fourth layer here we have is self attention mechanism. That's what I have given you an example of book reading. So the self attention mechanism is a core component of the transformer architecture that allow the model to weight the importance of different tokens in a sequence relative to each other. It helps the model to focus on the relevant part of the input when generating each word in the output. So what does it mean basically? So I have given you like life is good. This is that sentence which we are reading on a book. Now it is not necessary we should focus on each word or each character of that book. We simply focus on a conceptual ways. Okay, that life is good, we might be focused on life and good, and in between we will predict, okay, this could be the word or is or am or whatever it is. That kind of self attention mechanism is used in the decoder or normally, because whatever the tokens we will get lot of tokens as an input for next layer, and we will that model doesn't sure, okay, which token has more important for which model, which token we have to do a main focus. That's what the positional token help us in self attention mechanism to understand, okay, this token will have more importance and that token will have less importance. So that's how basically self attention mechanism work, and in that also mechanism we use some kind of formula, which actually I have not written over the slides because that is not useful to us, but it's good to understand, okay, there are formula which is used by, like each layer use some kind of mathematical functions, and based on the result, based on the output, each layer get provided to the input for the next layer. And this process repeats n number of times. So in a self attention mechanism there are three steps which it does, three what is called vector reduce, query, key and value. So each token's embedding is linearly transformed into three vectors, the q, k and v, query, key and value. So in these, whatever the tokens we have done in a positional embedding, that token will be transformed in each vector in this particular layer, self attention mechanism layer. So next we have attention score. So the compute attention score by taking the dot product of q and k, then applying a softmax function to that attention weightage. So these are the some mathematical terms which help us to get the proper output based on the input or based on the token which each layer will get from the previous layer. So if you see the example is chat is the current token. Self attention helps determine how much focus to put on GPT is and grade. So in a self attention mechanism, basically we are calculating the weightage of each token, and based on the importance or based on the weightage, it will start pass that tokens to the next layer. Next we have a multi-head attention mechanism. So the decoder multi-head attention mechanism consists of multiple attention head, by multiple headmaster, in a simple word we can say. each of which independently attend to the different part of the input sentence. So suppose we have, like for example, we have three headmaster, and each headmaster is focusing on a particular student. That this is in a simple word or simple language, that process called a multi-head attention mechanism basically. So each attention head learned different aspect of the input sequence, capturing the relationship between the token. For example, the cat sat on the mat. This is the input sentence which we have provided. So for example, one attention head might focus on the word cat and its surrounding context, while another attention head might focus on the word mat. So that's how basically a multi-head attention work. You can see we have provided some kind of input sentence here, and input token here basically, or any sentence basically. So each head will focus on a particular part of that sentence or a token, and it will output and it will provide the output to the next layer. That's how basically multi-head attention mechanisms work in decoder model. Next we have is layer normalization and the residual connections. So layer normalization and residual connections are applied to the output of multi-head attention layer. Layer normalization helps stabilize training by normalizing the output of each layer, and residual connection facilitates that flow of information through the network. These techniques ensure that the model can effectively learn from the input sequence and capture relevant information for gathering the output sequence. So each layer in a decoder only format, they are repeated multiple times after each layer until they will not get the proper output which they want. Next we have here is feed forward network. So the output of a multi-head attention layer is passed through the feed forward neural network with non-linear activation function. And one more thing, each layer does some kind of mathematical calculation, and based on the output, or based on the weightage, or based on the sum what they have defined in that particular layer, it will pass in that same sequence to the next layer. The token in the same sequence to the next layers. So the feed-forward networks enable the model to learn more sophisticated representation of input sentence and incorporating higher order interaction between tokens. So as we are coming from up to down, each layer is basically what is doing? It's basically polishing the each token, so we will get the proper or exact output which we require. The eighth, here we have linear transformation. So after passing through the stack of layers, like multiple of layers, the final output is transformed linearly to a map to the desired output size which we actually want, which is the size of the vocabulary. And the linear transformation is applied on which layers? Token embedding layer, it applies. What's the purpose here? Convert each token into the dense vector of fixed size. And again the linear transformation applied in the attention self attention layer mechanism layer also. Here what it does, it compound how much focus each token should have on every other token in the sequence. And the feed forward neural network, here basically what it does, applies additional transformation to data, allowing the model to learn more complex patterns. So linear transformations will apply multiple times. It's basically depend on the input what we have provided, and it will start calculating repeating each and every step until it will get the proper token which we want in as a output. Next we have output probabilities. So the output probability the output of linear transformation is a vector of raw score for each token in the vocabulary. So here what is the, whatever the tokens it got, it may pass to the vocabulary. And here what is happening, the output, so based on the token which we got from these particular layers, these scores are converted into probabilities using the softmax function. Again we are seeing here one of the functions, softmax function, which is applied. So based on the softmax function, we will get the final output which we want as a result. These softmax function normalize the score so they sum up to 1, turning them into the valid probability distribution. So these are the many layers which we have in decoder model, which is basically in background. This is happening in the ChatGPT model. So that's all for today. See you in next video. Thank you so much.